For energy to be conserved, there has to be a specific relationship between how the forces how the forces are directed, which result from the flow of currents in motional EMF situations. This can be summarized in something known as Lenz's law. There are actually a couple of variations of Lenz's law. What it boils down to in the end is something I normally would like to call the no free lunch law. Basically, it tells you that if energy is going to be conserved, you can't get like any free bonuses. That the current that you generate as you produce emotional EMF must somehow make it harder for you to move those wires so that you are actually having to put work into the system. You're not getting energy out for free. So what it tells you is that the motional EMF always generates currents right in the direction to produce forces opposing the motion. And we can see, in fact, how this works out in our specific example. If we go all the way to the top, back to our motional EMF example, you will notice that we had worked through this example very carefully and decided that as this circuit is being moved off to the right with velocity v, that the way the current moves through the circuit is upwards through this resistor. And what that implies, though, when we go into the field, is that there is a current flowing downward through this conducting element. Right? The current flows up through the resistor, across this wire, down through here, back through this wire, and then back up through that resistor. Now, this current must be inducing forces that are making it difficult for us to maintain this velocity. That's because those external forces must be necessary to maintain the velocity, because they are the ones that are inputting the energy that's ultimately dissipated in the resistor. And we can see that that is in fact the case. If we think of this current I that's flowing downwards, and we use our right-hand rule to determine the magnetic force on such a current, you would have your fingers oriented down the page along I, in a way in which you could curl your fingers upwards towards that magnetic field, and you would see then that the magnetic force from that situation would point you off to the left, so that IL cross B points to the left, and that sense of current flow then produces a force that tries to slow down this motion, so that to maintain it and continue to get this power, we have to put work into the system. It would be a wonderful world if it were the opposite, if the current actually ended up flowing in the other way, if the sign on the EMF were the other way around, and somehow we had current flowing that would further increase this velocity, we would have, in essence, a perpetual motion machine and would solve the world's energy problems. But life isn't that simple. So you can always quickly figure out which way the current is going to flow by simply thinking through, well, there are two possibilities, and you have to think through which possibility is going to oppose the motion. Now, that is the mechanical version of Lenz's law. There's also a Faraday's law, or electrical version of the law. So let me just label this one. This is the mechanical version, when things are moving. The mechanical or emotional version. There's also this electrical version. So this is the emotional version. The electrical version states that, and this electrical version goes with Faraday's law. So the electrical version states that the induced EMF from Faraday's law always would generate currents directed so as to create magnetic fields, B fields, opposing the change in flux. In the change in flux. So, more generally speaking, both of these laws find a way to oppose the change in flux. And we can see this electrical version actually also operative in the our second example that we had here, where we were moving the magnetic field. When we move the magnetic field this way with velocity v, as you can see, we are actually increasing the amount of upward flux here through our loop. Now, notice the direction of the current flow. The current flows again in the same direction as we had previously, so it flows up through here, across, then down through this perfect conductor, back across to the left, and then back up through this resistor. And if you think about this type of circulation of current flow, and you use your right-hand rule number 2, you will realize that the magnetic field lines associated with each of these wires are always generating magnetic field lines that go downward through the center here. Right? The magnetic circulation from the right-hand rule would come out in front and then down and back. In this one, it's the other way around. It's up and back and down in front. This one, the magnetic field lines would come around for you this way. And this one, the magnetic field lines come back around from this side and downward like so. In all of these cases, with the current flowing in this direction, this flow of this current tends to increase the amount of magnetic field going down through our loop. That downward extra contribution will create negative flux that's opposing the increasing upward flux that occurs because of the motion of that magnetic field. And this is, again, another reflection of the no free lunch law, and it also allows you to determine the direction of the induced EMF and the induced currents, because there are only two choices for that flow, and the other choice, of course, would give you the opposite conclusion, where as we're moving the magnetic field, we get an extra current which further enhances that change in the magnetic field. So that is the essential content of Lenz's law, which is a very important law for determining basic signs and directions in problems involving changes in magnetic field, either through motion or through actual changes in the field itself.